Hello, my name is Arjun, and my project is titled Real-Time Drowning Detection Using a Motorized Machine Learning Monitor System. This past August, my 18-month-old cousin slipped out the side of his house and fell into a pool. His parents were searching for him everywhere inside the house, and by the time they found him outside, he had been underwater for 10 minutes. They rushed him to the hospital, where he had suffered irreversible brain damage from the water that had gone to his head, and was brain dead for 10 days before he finally passed away. Now, after this happened, I decided to do some more research into this and learned that drowning wasn't just a tragedy faced by my family, but is actually the leading cause of death in children aged 1 to 4 years old in America, and that 50% of these deaths occur in swimming pools. In my project deals with developing a poolside monitoring device that uses real-time machine learning image classification to detect and alert users about potential drownings in pools. When I started this project, there were 3 unique goals that I aimed to accomplish. First, the solution that I create must contain dynamic hardware and must be able to collect a real-time visual and audio stream from all areas of the pool. Second, the solution I create must be optimized to maximize detection accuracy and speed in classifying drowning from images. And finally, the solution must create rapid alerting methods, including an integrated mobile alerting app and peripheral speaker and light system to rapidly alert parents and other homeowners of potential drownings. The constructed drowning detection system contains 3 primary components: the drowning detection device, the convolutional neural network, and the mobile alerting app. The drowning detection device is a waterproof poolside monitoring device that attaches to the side of the pool and is half above and below the water. It collects a real-time stream of visual and audio data from all areas of the pool and streams this to a back-end server in real time. Here, a convolutional neural network is used to analyze the images and audio and classify the given situation as swimming, drowning, or an empty pool currently being seen. Finally, the mobile alerting app is used to see a live status and feed of the pool, as well as enter in emergency contact information. The first step I took in this project was to create the drowning detection device. This device uses a camera and microphone to collect the necessary visual and audio data necessary to detect drowning. This data is streamed over Wi-Fi in real time to the back-end server, and also uses an integrated LED panel system and waterproof speaker to visually and audibly alert nearby people when a potential drowning is detected. The first step of constructing the drowning detection device was to create the linear actuator system, which is responsible for translating a camera and microphone above and below the water. To do this, I used a 2040 aluminum profile as well as a NEMA 17 stepper motor. The diagrams below show the individual parts as well as assembled linear actuator. The second step in creating the drowning detection device was to create the Raspberry Pi circuit. To do this, I used a Raspberry Pi 4 Model B with Wi-Fi connectivity and the Linux-based Raspberry Pi operating system. The camera is used to take images of the pool both above and below the water and at various angles. The microphone is used to detect trigger words such as help or I'm drowning, which augments the chance of the system detecting that someone is drowning. Finally, the LED panels and Bluetooth speaker component of the Raspberry Pi are used to flash and play an alarm noise when a potential drowning is detected, and the stepper motor and servo motor are used to actuate the system above and below the water, as well as rotate the camera 180 degrees. Because the drowning detection device is semi-submerged and subject to constant pressure from the pool, a waterproof plexiglass casing was constructed. Due to its durability and transparency, plexiglass was used as the primary material. A power jigsaw was used to cut it into individual cross-sections, and silicone sealant was used to assemble it into a final case, and 5 suction cups were added to the bottom half of the backside, which would allow it to attach to the side of a pool. This case was allowed to dry overnight before the mechanical and electrical hardware was added inside. The constructed drowning detection device takes 17 seconds for one monitoring cycle, in which it actuates above and below the water and streams a real-time visual and audio data from all areas of the pool to the back-end server. Now that the collected data was being collected and sent to the back-end server, the second step of the project was to create a novel approach to analyzing all of this data. To do this, a convolutional neural network, or CNN, was created. A CNN is a type of machine learning image classification model which takes an input image and passes it through various convolutional layers, which learns more about specific features of the image and classifies it into a given class. In this case, an input image is received from the drowning detection device camera and is passed through the convolutional neural network to classify the situation as either swimming, drowning, or an empty pool being seen. In the back of the convolutional neural network, 4 primary hidden layers are used to make the prediction of whether a given image is a swimming, drowning, or an empty pool being seen. Linear equations, as well as an activation map and feature map, are used to learn more about specific features of the image and produce a final output of swimming, drowning, or an empty pool. Now that the data of the pool was being collected and analyzed, the final step in the project was to create a way for users to actually see the live feed of their pool, as well as get rapid alarms signaling for help when a potential drowning is detected. To do this, I constructed a mobile alerting app using the Swift programming language and Apple Xcode development environment. The shown app contains 3 pages. The first page, which is the live feed page, allows users to see a current status and feed of their pool, as well as the ability to rewind and see previous feed of the pool. The second page, contact information page, allows users to enter in an emergency name, address, and phone numbers to be contacted with when a potential drowning is detected. And finally, the simulate page allows the users to test the functionality of their drowning detection device. After constructing the system, range of visibility tests were ran. First, using calculations of the camera resolution accuracy, it was found to contain an 81.5 degree field of view per image of the camera, as well as an average resolution accuracy of 95,000 pixels per square inch, which is high enough to see even minor changes in facial expression, body position, and body movement. Next, when it came to testing the hardware range of translation and rotation, the drowning detection device was found to contain a 20-inch range of vertical translation, as well as a 180-degree range of horizontal translation and rotation as well. This 20-inch range of vertical translation and 180-degree range of horizontal rotation allow the system to be scalable and implementable regardless of increasing pool size or varying pool shapes. To test the drowning detection model, a custom data set first had to be created. To do this, I downloaded over 750 images of swimming, drowning, and empty pool images, both during daytime, nighttime, above and below the water, and including people of all ages and genders. This data set was used to train the machine learning model, and after 200 training cycles, the model reached a final accuracy of 96.35% accuracy, which is a strong preliminary success with room to approach ideal accuracy in some classification accuracies in residential pools. As shown below, the 3 sample images of either swimming, drowning, and empty pool are sample images that were used to train the model. Below that, the progression graphs showing the increasing accuracy and decreasing loss of the model during training show high success of the model with room to grow. On the right, finally, you can see 2 accuracy metrics and 2 error metrics, which show a promising success of the model with classifying swimming, drowning, and empty pool images. In conclusion, the drowning detection system and drowning detection's device has the ability to save lives by detecting drowning in pools in real time and entirely remove the human supervision requirement of pool safety. Currently, the system operates at an accuracy of around 96% and loss of 8%, as well as containing a resolution accuracy of around 90,000 pixels per square inch, as well as 20-inch range of vertical translation and 180-degree range of horizontal rotation. This ensures that the drowning detection device will be dynamic and scalable and able to monitor all areas of any residential pool. Additionally, this system can save thousands of lives and prevent irreversible damage to a victim's health by potentially solving the drowning crisis at the root of its problem. Going forward, some plans for future and further study involve switching the drowning detection device to a renewable energy source, as well as testing the drowning detection system in a real pool. Additionally, implementing sonar as an additional method of data collection and using 5G as a new method of data transfer would also be very beneficial to the system. Finally, augmenting the data set with more images during nighttime would make the machine learning model more dynamic and capable of recognizing drowning in all situations. Thank you for listening to my presentation.